Okay, yeah.
Oh, yeah, recording, yes, yeah.
Okay, yeah. Okay, so we just continue from where we ended yesterday.
Okay.
Yes. So yesterday we looked much on the quantification of water and the soil itself in terms of what parameters we can use to measure the soil in terms of its mass, in terms of its volume.
Yes.
So,
Mhm.
so today we'll look at more on the degradation of soil, the functions of soil, and the degradation of soil.
Oh,
So
okay.
yes, we looked at the soil, its composition, and its properties. So now today we'll now look at what are the functions of this soil.
Okay.
So we can classify uh, uh, the functions of soil. We can break them down into seven broad categories.
Mm-hmm.
Yes. So the first one is obviously for biomass production, like for crop production, maize production, and other agricultural things. We know that we usually use soil to grow our crops because it provides nutrients, it provides soil water, and just the anchorage of plants. So that's the first
Okay.
use of the soil. So we'll look at these functions, and these functions are going to lead us now into soil conservation because we want to conserve soil so the soil is able to carry out these functions. So the first one we
Yeah.
said is for biomass production. I think that's the most obvious one. Then
Mm-hmm.
the second one says it's used for storing, filtering, and transforming nutrients. So
Mm-hmm.
what they mean here is that the soil stores nutrients. Like that's where you
Mm-hmm.
find nutrients, the nitrogens, the potassium, and things like that. They are held on the soil surface, such that when you take a soil, you take it to the lab, you'll be able to find these nutrients. So they are held on the soil surface, such that plants are able to access them. Then it's
Mm-hmm.
also a filtering substance, meaning that if you have, for example, a pollutant, like a water which is polluted, as it is passing through the soil will start to absorb those pollutants, such that as that water reaches the groundwater, it has become pure again. So soil is
Yeah.
used as a purification substance. It filters water as it goes into groundwater. Then it
Okay.
also transforms nutrients. For example, if you have organic matter, nitrogen changes from different forms. So it changes from the organic form into the inorganic form in the soil. So soil acts as a body where this transformation will take place. So that's another function of soil to store, filter, and transform nutrients.
Mm-hmm.
Yes. Then it's also a biodiversity pool, meaning that you have different microorganisms in the soil, the bacteria, the viruses, the earthworms, and things like that. So you have different species of microorganisms that are found, but also it's used for human activity where people put their homes and build
Mm-hmm.
shops and things like that. Yeah, and
Okay. Yeah.
yeah, the other one is raw material. Those who want to build and use it for construction. Then another
Mm-hmm.
important one is it acts as a carbon pool. So in the
Yeah.
soil, that's where you have carbon is stored, such that if you bring a land into cultivation, most of the carbon is lost to the atmosphere, and you have now this issue of climate change and things like that. They are all stemming from the same loss of carbon from the soil. So the soil acts to store carbon in the soil so that it doesn't escape to the atmosphere. Then the other use is soil acts as a geological and archaeological heritage. So you find that most historical stuff is found in the soil. Maybe the Stone Age people, when they start to dig, they find those equipments which they used to use and things like that. So soil acts to store geological and archaeological items which were used in the past. So broadly, these are the uses of soil. But for us, we focus mainly on the first one, the second one, the third one, and the sixth one. These are the ones for raw material. This one, the one for raw material is more on the engineering part, as well as the human activity and the archaeological, the geological and archaeological heritage. So these ones are more on the engineering part.
Okay.
Yeah, and not more on the environmental part.
Okay.
Yeah.
On the carbon sink, I think I've understood Yama plants as carbon sinks.
Okay.
Now on the soil, how does it act as a carbon sink?
Or the soil itself?
Is apart from the storage.
Yeah. So it's you can relate it to plants as well, because it's if plants are going to grow in the soil, then it means that for that plant to grow, there should be soil first, and then that plant, for it to carry out that function, it will need a soil as well. So you can relate it to that as well.
Oh, okay.
Yes.
All right.
Yeah.
Okay.
Yeah.
Now clear now.
Okay. Yeah. So now we've discussed the uses, the functions of soil. So if a soil is doing all those functions that we have listed, we are simply saying that this soil is a healthy soil. It's a good soil because it's able to carry out these ecosystem functions. But now when this soil those functions start to reduce, like if it cannot carry out those functions, then now we say that the capacity is starting to reduce, meaning that we can say now that the soil is becoming degraded. So we can define degradation as the reduction in the capacity of the soil to perform its functions. So the moment it starts to fail to perform its functions, we say that now this soil is becoming degraded. But yeah, but in the actual definition now, we can simply say that soil degradation is a deterioration of the soil physical, chemical, and biological characteristics, thereby reducing its capacity to perform functions. So it's deteriorating in its physical, chemical, and biological characteristics, such that now you are not able to use it for crop production, you're not able to use it for filtering, you're not able to use it for carbon storage and the other functions. So when that happens, now we say that this soil is degraded. But for this course, in as much as there is physical degradation, chemical degradation, and biological degradation, we're going to focus more on the physical degradation. So the chemical and biological, will not discuss much about that because this course is mainly for the physical degradation.
Okay.
Yes. So the physical degradation meaning that it's the actual framework of the soil, that inorganic part that we saw, which we said is the framework of which holds the other components together. That physical characteristic that we're able to see, that's what we focus on. So the main processes that come with this physical degradation is one, soil compaction, soil crusting, and soil erosion. So look at these three processes which deteriorate the soil physically.
Okay.
Yes. So we'll start with soil compaction.
Okay.
Yes. So before we define soil compaction, we would need to understand the concept of soil structure. So soil structure is the arrangement of soil aggregates, of soil particles, sorry, to form an aggregate. So you have individual soil particles, but these soil particles will stick together to form an aggregate. So when they form an aggregate like this one, you see there are different small pores, small particles held together. Then they are leaving these spaces, the white ones, in between. So these ones are what we refer to as porosity in the yesterday's lecture. So
yes, okay.
this is where you have air and water.
Water.
Yes, in these four spaces.
Okay.
Yes. So the arrangement, this is what we refer to as soil. This is an aggregate. So this is the structure of the soil. Now the arrangement of small particles to form this aggregate. So these pores are important because of air circulation and water circulation. So you need a soil to have a good porosity for it to function well. So when you are talking of porosity, there are two types of pores that we're talking about. If you can see in this diagram, these small brown, the brown things, these are soil particles. Then this, what is connecting them? These are like cementing agents. So they're the ones that are making the soils to stick together. So this can be organic matter or sesquic oxide. It's another cementing agent which holds the soil together. So when it holds the soil particles together, there are two types of pores which result. So if you have this small aggregate, okay,
yes,
it has small pores inside here.
Yeah.
So these ones we call the micropores. Then if you have these three aggregates here, when they are put together, you find that there are these big spaces which are going to be left.
Okay.
Yeah, these ones are called macropores. So there's micro and macropores. So these big ones, they are important because this is where water will be moving. So they're important for water and air transmission because they are bigger, so water is able to move and air is able to move. But these smaller ones, these what we call intra-aggregate, because they're
Yes.
within the aggregate. So intra-aggregate pores, these ones mainly because they are smaller, they are used to store water.
Oh, okay.
Yes, so the big ones, the inter-aggregate or macropores, they are used to transmit water and air. Then the smaller ones are used to store water.
Okay.
Yes, so those are like two types of pores and their
Oh,
functions.
all right.
Yes. So now that we know that, okay, soil has these pore spaces in between, and these pore spaces are meant to transmit water and to store water and to also transmit air. So mean that if you
Yes.
have a good porosity, it means that the soil will be able to you'll be able to grow plants in there because there's enough water and enough air. So
Yeah, okay.
now we can talk of compaction, which is simply the breakdown of this structure of soil. So if a soil breaks down such that these pore spaces that we had are no longer there because now, like we've compressed it, such that these
Mm-hmm.
pore spaces now are reduced or they are no longer there.
Yes.
Now we say that this soil is compacted.
Okay.
And now, since it's compacted, the pore spaces are reduced. The bigger pores, they are reduced as well, meaning that there will be no transmission of water, no transmission of air, but also the small pores again where water was stored will be reduced as well. So
Mm-hmm.
compaction, we can see it as because if you have a volume of soil with the pore
Yes.
spaces, then when you compress
Mm.
it, so if you have a soil, for example, in a cup,
Yeah.
then it has a good structure for it, right? Then
Yeah.
the mass of that soil, you measure it. Then you also measure the volume in which it occupies. Then we decide to compress it. The mass of
Mm.
the soil will remain the same, but because we've compressed it, the volume will
Yeah.
reduce.
Reduce. Yeah.
Yes. So when that happens, you remember we said that the bulk density was the mass divided by the volume.
Yeah. Mass of solid phase over the total volume. Yeah.
Yes. So if the
Okay.
volume now, we've compressed it, the volume has reduced, it means that the bulk density has increased.
Increased. Yes. Oh,
Yes.
yeah. Yeah.
Yes.
Mm.
Yes. So when we
Okay.
say compaction, we can also say
Yes.
that this is the increase in the weight per unit volume of soil, or simply saying it's the increase in the bulk density of the soil.
Okay. Thank you
Yes,
very much. Okay.
yes. So uh, if, for example, I ask the question, what is soil compaction?
Yes.
You can say soil compaction is a breakdown in the structural makeup of the soil, which reduces
Mm.
its volume. Okay,
Okay.
or you can
Yes.
simply say compaction is a reduction in, or you can simply say compaction is the increase in the weight per unit volume of soil.
Unit volume of. Okay.
Yeah. So as long as you just understand what's happening when you
Yes.
say soil is being compacted, then you can define it in whichever way that you feel. But the consequence is that it reduces air capacity, water capacity, and the transmission.
Okay.
Yes. So if we look at this uh, this diagram here, it's basically what I was
Yes.
talking about. If you have a non-compacted soil, it fits
Mm-hmm.
a certain volume here. So it has soil particles, and it has these white areas where there's air. So if we
Yes.
compress this volume to, like,
Yes.
from here to here, the mass will remain the same, but
The volume.
the volume of air which was occupied by the air now has reduced.
Just
Yeah, so now we are saying that it has a higher bulk density.
density.
Yes. So like we said, so compaction will increase the bulk density. It
Density.
will reduce,
Loss of air
yeah,
capacity.
less air capacity, as well as the water capacity. Yeah. So that's uh, 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 one of the causes of soil degradation, which is compaction. And now,
Okay.
what will cause the soil to be compacted? There are various things that we can attribute it. One of them is inappropriate tillage practices. So,
Mhm.
yeah. So when we talk of measures of soil conservation, we'll be actually talking of appropriate tillage
Mhm.
practices. Which practices can we do to avoid soil degradation? So one of them is
Okay.
this one. We'll look at it when we come to the measures. But if you have practices which destroy the structure of the soil, then it will lead to compaction.
Okay.
Yeah. Then also use of machineries. If you are using big machinery on your farm, and
Mhm.
you're using them maybe when it's wet, like the tractors and things like that, they will begin to compact your soil.
Mhm.
Yeah, as well as if you have a lot of animal traffic on your farm, it's also another cause of compaction.
Okay.
Then, yeah, of course, if you have loss of organic matter, meaning that that structure of the soil, you are not able to build it because organic matter will act as a cementing agent. But if you don't
Mhm.
have the organic matter, it means that your soil will start to lose its structure and it will start to compact.
Mhm.
Yeah, then sodicity, if you have a lot of sodium in your soil, the soil begins to disperse, and then it
Mhm.
will, yeah, to start to compact. So it's,
Okay.
yeah. So this is a chemical cause of physical degradation. So the concentration of sodium,
Oh.
the higher the
Mhm.
sodium, the more the soil loses its structure. Like the soils we saw in Lucitu there.
Yeah, receipt. Yes.
Yeah, yeah, because of the sodium.
Mhm.
Yes. Then
Okay.
the second form of degradation that would look at is soil crusting and sealing. I'm sure you've seen soils that produce a hard layer on top, like these ones here.
We have them here.
Yeah, yeah, yeah. So, so this is what we call crusting. And usually,
Yeah.
when they form that hard layer, it's usually difficult for plants to germinate or
Mhm.
for water to penetrate. So
Mhm.
this is a form of degradation, but it's usually associated with a type of a soil.
Yes.
Yeah, it's usually associated with a type of soil. So in most cases, soils which are like this are not supposed to be left bare. So there's supposed to be always
Okay.
a protective cover on top so that you prevent this phenomenon from occurring. So if it happens like
Okay.
that, it means that you have restricted water entry into the soil, and also air will find it difficult to go in because the top part is like sealed. So the pore spaces, they are also filled
Yes.
on top. And this usually happens when you have, for example, you have rain, and then rain as it comes, it disintegrates the soil particles at the surface. Then these small particles now go to fill in the pore spaces on the surface of the soil. So that's the second form of degradation.
Okay.
Yes. Then the last form of physical
Just
degradation.
is there any difference between crusting and compaction?
Yes. So usually when we talk of there is a thin line, because when you talk of crusting, we are simply saying that it is just the top layer. The top layer, we are referring to the top layer of the soil. So yes, you're right. You can say crusting is the compaction of just the topmost layer.
Okay.
Yes, but when we talk of compaction, it can occur anywhere in the soil, whether it's in the subsoil or it's in the topsoil. But if we say crusting, we are referring to the top layer of the soil.
Yeah.
Yes. So yes, you're right. The only difference is that crusting is at the top, but it's also a form of compaction, because the top layer now is becoming compacted such that water is not able to go through.
All right.
Yes.
Then compaction physically it's difficult to see it with your eyes.
Yes, it's difficult to see it with your eyes unless you can have indicators which can show you. For example, you can use plants, for example, to show that okay, these plants you're watering, but maybe the water is just running off. So you suspect that maybe the soil is compacted and water is not able to be transmitted because the pore spaces are less. But the best way now is either you get a sample and you measure the bulk density, or you use a penetrometer.
Penetrometer. Okay.
Yeah. You know a penetrometer? It's a device which you
Yeah.
you've seen it before, right? So it just gives you how hard the soil is.
Okay.
Yeah, so you try to force it into the soil, and depending on how much energy you're using to penetrate the soil, it gives you a value of that force that you are using. So you're able to use that value to say, okay, now this soil compared to this one is more compacted than this one.
All right.
Yes.
Okay.
Yeah. So when you're in the field, you can use penetrometer measurements to determine whether the soil is compacted. Then when you're in the lab, you can do bulk density measurements.
Okay.
Yeah. Yeah. So the last form of degradation that we're going to look at is soil erosion. So this is just simply the removal of topsoil by wind or water. But for example, here in Zambia, most of the erosion is as a consequence of water movement, and it's usually accomplished in three stages, where you have first the detachment of particles. For example, here when the rain is coming, it's hitting into the soil, so it's breaking the soil particles. Then as it breaks, it starts to transport them until it deposits them at the lower end. So because this process is it's a three-stage process, it's going to have a consequence on the management practices, because us, we are interested in
Practices.
conserving the soil. So it means that when we look at these three stages, we have to see at each stage what measure can we put in place. For example, if we see that, okay, here where the rain is breaking down the soil, it means that if we want to control erosion from here, we can easily put a cover here, such that as the rain is hitting, it's not able to hit the particles. But also, if we want, we can say, okay, we can control it during the transporting stage, where we can grow grass here, so that the soil particles are not able to move. So it will have a consequence on what measures we're going to use. So like we discussed in the previous course that we had, that erosion will have factors that will affect it, like the slope. Like the steeper the slope, the more water will be sliding on that slope, and it's carrying with it soil. So if you have a slopy soil, the erosion will increase. Then the second one is organic matter. Organic matter, you can look at it in two ways. First of all, we said it acts as a cementing agent, meaning that it holds the soil particles together. So if it holds the soil particles together, it means that they cannot be disintegrated. And if they're not disintegrated, then they can't be carried by the soil, by the water. Same with structure. So for structure, again, we can look at it in two ways. We can say that structure, if a soil is well structured, it means that the soil particles are well held together and they cannot be transported by moving water. But also, if your soil has a good structure, it means that it will have a lot of pore spaces. So instead of water sliding on top of the soil, it will be infiltrating, meaning that you have less water running off on your surface. Then vegetative cover, obviously, this now will block the soil from moving, to block the water from moving, and consequently, the soil will not move. In land use, this involves different, if, for example, your land use is such that it clears the whole surface of the soil from vegetation, it means that you have a lot of, it will be exposed to soil erosion. So these are the factors, and these factors now help us to determine how much soil can be lost in a particular field. So this equation is the one that we looked at even in the previous course. So it's just estimating, estimating the amount of erosion that can take place. So it's a function of the rainfall erosivity, the soil erosivity, the slope, the crop management, and the
management practice.
The management practices, such that when we start to look at the different soil conservation measures, you should be able to relate it to this equation, to say, okay, this management factor, how is which parameter is it affecting? Is it affecting the C factor or the P factor, or it's affecting the LS factor? Then so now you should be able to explain the mechanism with which it's reducing the soil erosion. So this graph is for simply showing the how to to determine the LS factor. So it's just a function of the slope and the length of the slope. So here you have the length of the slope.
Okay.
Like for example, here if it's 300 meters, then you go to your slope. For example, if your slope is 10, then you can get your LS factor on this axis.
Yeah.
Yeah. So when you're dealing with, for example, this universal soil loss equation, and for example, you're given two fields. You're saying that this field is upland, this field is in the lower area. So if you're asked to calculate the soil loss in the first field, you calculate it normally using this equation. But now when it comes to the total catchment, it means that when you have a soil that is being eroded in the first field, it's going to pass through the second field. Okay. So if, for example, you have a management practice in the first field, in the second field, it means that the soil which is coming from the first field, as it enters the second field, that soil will not be lost because it will be only part of it, of course, will be lost, but the other will be conserved.
Deposited.
Yeah, in that field. So if you're looking at the erosion of the total area, it means that first you calculate the erosion in the first area, then when calculating the erosion in the second area, you have to consider that that soil which was coming from the first field, not all of it is going to be lost.
Okay.
Yeah, so you look at it in that way when you're analyzing such kind of problems. Yeah. So now that we have looked at these three forms of degradation, we have compaction, we have crusting, and soil erosion. The question now will be, what are the consequences on the environment? So obviously, when we're talking of compaction, the soil air capacity and water capacity is lost, meaning that we cannot, it will be difficult for us to grow crops because the crops need water and air. It will also be difficult for plant roots to grow because the soil is hard, so they won't be able to pass their roots. But also compaction itself will encourage erosion because water is not able to penetrate. It will start moving on the surface of the soil, and it will erode the soil. Then erosion itself, because it's taking away soil from your field, it means that you can't plant because your soil has been eroded. It means that you lose your organic matter. You lose your nutrients. And if the soil is lost, it means that it can't perform the function of storing carbon. It can't perform the function of having microorganisms in the soil. So the consequence of this degradation is that it reduces these functions here that we talked about.
Oh, okay.
Yeah, so if the soil is able to perform these functions, it's a healthy soil. If not, it's a degraded soil. Such that the consequences of the degradation are those functions that we talked about.
Okay.
Yeah. So as we go into the next chapter, which is soil conservation now, we are looking at ways in which we prevent soil degradation. So we are looking at ways in which we prevent soil compaction, soil erosion, and soil crusting. So if, as we are going to be looking at each measure, you should be able to relate it to this universal soil loss equation, as well as
Okay.
the process of compaction.
Okay.
Yeah. So I think we'll. This is what I wanted us to cover today.
Okay.
Yes. So I think we'll pick it up from tomorrow. So this we have finished the first unit.
Unit.
Yes, the first unit in the module. So tomorrow we'll go into the second unit, which is now
Okay.
soil conservation. So basically we'll just be looking at the measures which we can put in place to prevent the erosion, compaction, and crusting.
Okay.
Yes. So I think we'll end here for today.
Okay.
Yes.
Okay. I think it's a good unit.
Mm.
Unit 1.
Yeah.
But on the calculations, we'll look at bulk density examples.
Yes. Maybe we can just go through one or two, which from the module we just go through.
Okay.
Yeah. Let me just.
There will be. Could it be beyond the module?
No. So.
Yeah, many examples there.
Yeah. So basically, if, for example, from unit 1.
Yes.
From unit 1, if there will be calculations.
Yes.
Let me see. Well, this one is not much of calculation. So maybe this one, YAML pedu transfer functions.
Yes.
Yeah, but for this one, we're going to see the application Kambocha water conservation. Because, for example, if you have to calculate these values, when you calculate these values, you have to use them in maybe in a irrigation schedule. So, but
Yes.
basically these are not difficult calculations, because you just plug in the missing values. But maybe what you might need to understand, maybe it's just this part, these calculations. For example,
Yes.
if you're given a certain bulk density, what is the porosity?
Yeah.
Or if you are given this porosity, what is the bulk density? So you just relate to these ones. Then also maybe you are given a soil, a dry soil, and also its volume. What is the bulk density? Or what is the or what is, so if you're given a dry soil and the volume, then maybe you ask what is its porosity. Then, for example, if you're given two soils, you're asked, okay, you calculate the porosity for this one and this one, then you ask, okay, what's the consequence? Or why do you think this soil is like has a lower porosity than this one? Then what can you do to improve such a scenario? Yeah. Then also maybe these relationships for relating gravimetric moisture content to volumetric moisture content. Yeah, where you, for example, maybe you'll be given a moisture content, but it's in gravimetric. Then if you had to use it in a calculation, for example, in which it's supposed to be in a volumetric moisture content, so you just simply multiply it with a bulk density.
Bulk density, yes.
Yeah. Then, for example, this one, the example that we saw yesterday, we're going to see it again when we start doing in water conservation. So it will become more clear when we go when we go there. So, but the calculations that I wanted us to go through was on Let me just share this one. In the first unit was on just how to derive this module, how to derive those relationships. So, but I think as you go through the module, it also explains how these things are done. So you remember we said that porosity can be calculated as 1 minus bulk density over particle density.
Okay. Yes, I went through these.
Ah, okay, okay. Also, okay, this one, so you're able to you
Yes.
understood why this why porosity came to this formula. So, for example, we said that the volume of the volume of air, the volume of liquid and solid equals the total volume. So if we have a ratio of these ones to the total volume, it will give us 1. Okay. Yeah. So, but we also said that the volume of air and liquid, we can classify it as the volume of pores.
Of pores, yes.
Yes. So if we say because this is a fraction, we can separate it to say like V over T plus VL over T plus VS over T. So this is what we have done, except that we have added these two. And we know that the volume of pores, the volume of pores over the volume of total will give us porosity.
That's
So
porosity. Porosity, yes.
Yeah, this is porosity. So we can write it as porosity plus the volume of solids over volume total is equal to 1. But now we know that this volume of solid, we can write it as mass of solid divided by the density of the solid.
Yes.
So if we replace and also this volume of the soil, we can also write it in terms of the mass of the soil
over the total bulk density.
Over the total bulk density. So we can write it in this form. So this one in this form and this one in this form, such that when we replace them in this equation, we replace them here and here, you find that this mass of soil will cancel out.
Cancel each other.
Yes, and in the end now, you're going to remain with just the bulk density and the density of the particles of the soil. Yeah, which is the particle density, such that now your equation for porosity is going to come down just to this. So that's how they actually derived it. So this is just to help us understand why we can be able to do it that way, to just calculate porosity using that formula. Then the other one, the other derivation is the one where we say volumetric moisture content is equal to gravimetric moisture content times the bulk density. So what we can
density.
Yeah. So we can start from where we say, okay, gravimetric moisture content is equal to mass of water divided by the mass of soil. Then these masses of soil, we can rewrite them based on the formula for density, such that the mass of For example, mass of water here, we can say mass of water is equals to the density multiplied by the volume.
Oh
So
yes, mass is equal to density times volume. Yeah.
yes, so if we replace density of, so here to be the density of water minus the times the volume of water divided by the density of the bulk density of the soil multiplied by the
Yes.
total volume. So
Okay.
so it's going to become like this.
Okay.
Like the density of water multiplied by the volume of water divided by bulk density and the volume of water, such that
Okay.
because this on top is a, like multiplying, and this one is also
Yeah.
multiplying, we can rewrite it like this, where we say density of water over the density, the bulk density multiplied by volume of water over volume total, such
Okay.
that this one here
Yes.
is the definition of the volumetric moisture content.
Content. Okay.
Yeah, so remember we said the
Okay.
volumetric moisture content is the volume of water
Yes.
over the volume total. So we can simply
Yes.
write,
Volume of water.
yeah, we can simply write this as volumetric moisture content as it is in this equation. But
Yeah.
of course, we know that this the density of water is 1. So if you want, we
Yes.
can, yeah,
Yeah.
we can do away with it. But
So it's just
rearrange,
okay.
yeah, rearranging this formula such that we want to make volumetric moisture content a subject. It simply means that we multiply gravimetric moisture content with the bulk density.
Yeah. Bulk density.
Yeah, but since we said the volume of water is 1, we can just ignore it, and the formula now will become just like this. Volumetric
Okay.
moisture content is gravimetric moisture content times bulk density.
Okay.
Yeah, so this is just to show how that relationship came came about.
Okay.
Yeah. So I think for in this unit, those are the calculations that are there. But so in your I
Okay.
think in the assignment is where you're given a dry soil and a wet soil. You
Yes.
have to calculate
Oh,
is it the bulk density and the the, the
yeah.
moisture content. So you can use this procedure, this procedure that
Okay.
we have given here, where you say, okay, the volume of water, the mass of water, and the mass of water over the mass of soil gives you gravimetric moisture content. Then you multiply it with the bulk density to give you volumetric moisture content.
Okay.
Yeah. So
Mm.
so I think when you just go through this, then it will be easy to go through the that assignment. So, but basically,
Assignment.
yeah. So
Yeah,
basically,
nayo wanachapa
uh, so basically, my calculations, they will come in when we start to do water conservation.
okay.
Yeah, because that's when now we need to say, okay,
No problem.
yeah, that's when we need to say, okay, how much water should we add so that we don't waste?
Yes.
Yeah, things like
Yes.
that. Yeah. Then also maybe na
Oh.
pama erosion, you like,
Mm.
yeah, there will be, you would need to calculate maybe how much soil is going to be conserved if we use this practice. But the important thing is to know which practice is suitable for what kind of situation. So even if you have a calculation, what will be important is now if you calculate a number, what does it mean?
Okay.
Do I need to if I have this number, do I need
Yeah.
to do this practice, or this number, does it mean that this practice is better than this practice? So it will be more on the
Oh.
in the interpretation than in
Yes.
the actual calculation. So even if you do
Okay.
it, even if you do a calculation, then you find a wrong answer per se, then what you interpret using that number
Yes.
is what is important,
Yes.
because
Okay.
what's happening now, for example, is like we were talking yesterday, is that we have computer softwares which are
Yes.
used
Yes.
to do most of the calculations. But when you have
Yeah.
a result of the calculation, it is you now to say, okay, I have this number here. What does it mean? So, for example, you say you have the tensiometers that you have put in your Zambia sugar. If we say, okay,
Yeah.
it's 50%, what does it mean now? What should you do? So
Yes.
that's the whole idea of this course. So even if you have a wrong,
Oh.
even if you have a wrong calculation, you've plugged in the wrong values. But what is important is
Yes.
for you to interpret a number
Okay.
that you get.
Okay.
Yeah. So as long as you just know the principle of, okay, if we're saying what is soil compaction, you know, okay, soil compaction means this. So if you do a calculation and then you find that you do a wrong calculation, and then maybe you're comparing two soils, the bulk density of two soils, but you make a wrong calculation. But if you have two values that you calculate, maybe they are wrong, but you're able to say that, okay, in this soil, there will be less water capacity or less air capacity. Then it means that you've understood. Because usually what happens is that when you're working in a group, usually you work in a group. So when it comes to things with calculation, you don't do it alone. So if you're in a
Yeah.
group, obviously, if you make a mistake, someone will be able to spot, no, 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 there it's like this. But now,
Yes.
in the end, it's what you do with those numbers, how you
Yes.
interpret them is what is
Yes.
important. So I think we should look at it in that approach.
Okay.
Yes.
Okay.
Yeah. So I think we can end here for tonight. Then tomorrow
No problem.
we can continue. So the one for
Oh.
tomorrow, I think it doesn't have any calculations. It's just we're just looking at methods. Then
Okay.
yeah. So maybe when we come to Friday, maybe that's when we'll need to move a little bit slower so that we grasp the concepts of some, if there'll be any calculations. They are not
Okay.
they are not much calculations as well.
Yes.
It's a lot of, there's a lot of theory, but the calculation will just be there for you to appreciate, like okay, how now can it be done in real life? So that's where now
Yes.
you start to have those calculations. But since, because for
Okay.
example, the calculations, you just need to know the principle. Because for example, we're talking of that software that you have for irrigation at Zambia Sugar.
Yes.
So that
Yeah.
software will do all the calculations,
Yeah.
but the idea is just for you to know what, okay, if that software makes a mistake, you should be able to interrogate, to say no, I don't think this answer is correct.
It's correct. Yes.
Yeah, things like that. But the calculations and everything else it will do. So
Yes.
for you just to know the the principle.
Okay.
Yeah,
Mm,
yeah.
no, no problem. Actually, yes, clear.
Mm, okay. Okay. So
Mm,
I think we can end here for today. Then tomorrow
okay.
we'll communicate what time we'll be able to do the the, the lecture.
All right.
Yeah. So maybe I don't know how your weekend is. We can also have a class per weekend.
Yeah, yeah. Actually, weekend is even better.
Oh, okay, okay. Because I was thinking because this course is not
Yeah,
uh, uh, it's not bulky. It's not bulky because,
yes.
for
Yes.
example, when you look at the module, it looks bulky because of
Mm,
the elaboration on the practices. But
yes.
for example, if I was to explain the module,
Mm,
it will be short. It will be short because it for example, if there's a practice, I'll just say it. I'll just go direct to the point. But in the
yes.
mod,
Yeah.
you try
Mm,
to explain because there are those people who are seeing those things for the first time. So it has to
yes.
explain from
Mm,
the scratch. So I was thinking that
okay.
if we can do per weekend, it's possible
Mm,
we can finish the mod such
okay.
that next week we do the software and then
Yes.
we do a few example calculations.
No problem.
Yeah, yeah. So we can let's just communicate and see which how we can do it tomorrow and Friday.
Okay.
Yes.
No, no problem. Yeah, weekend is, yeah, it's fine.
Yeah, yeah. Because
Mm,
even the last unit is short.
yes.
It's
Yes.
short and
Mm,
it's I think it's that one even if we don't go through the module, it's something which is
mm,
because it's a social economic topic,
yes.
so it's
Yeah. So you can
more,
just,
yeah, it's more subjective
yeah.
than factual. So but then
Yeah. Mm,
we'll run through it and then we'll see how far we go.
okay.
Yes. Okay, so
Okay.
we can meet tomorrow afternoon.
All right, Mr. Mitzi.
Mm,
Thanks a lot.
okay, no, yeah, very welcome.
Yeah, I will let you know tomorrow. Yeah, I think Mazulu tingakwanisa nisa otherwise.
Okay, okay, all right. No
Yeah.
problem.
All right.
Okay, have a good
Thanks a
night.
lot, sir. Have a good night too. Thanks for sacrificing your time.
Okay, no, yeah, welcome.
Thank you.
Okay,
Yeah.
thanks.